Hey guys, welcome back to our live stream here at All Things Off Grid. We're just going to talk a little bit about solar and some battery basics right now, since that's usually what we talk about on our live stream here. One thing that was of interest for me, especially in the last couple of months here, if you guys have been following my TikToks over at CES and RE Plus, there are some other potentially interesting battery chemistries and technologies that are coming online in the near future here, especially when it pertains to us guys living off the grid. One of the most important aspects of living off the grid, I mean, it really comes down to two things, right? It comes down to water availability and power availability. When it comes to power generation side, our most common options these days are solar and some kind of turbine, whether it be wind or hydro. Now, having said that, obviously you have to store that energy somehow if you want to use that electricity throughout the day, throughout the night, throughout inclement weather. So one of the biggest investments that most of us guys that live off the grid do, and it's not just guys who live off the grid. In fact, a lot of my followers who subscribe to my information about batteries, they live on the grid. One of the challenges here in California is electricity is just really freaking expensive. Just to give you guys an idea, the cost of electricity, I mean, we can pull up a screen here to see what the time of use, SCE time of use rates look like. And just to give an idea of how much it costs here in California. So if you see these numbers here, covering my face here, you can see that during the winter it can range anywhere from 27 cents to 54 cents per kilowatt hour, and during the summertime it can be as low as 28 and as high as 61 cents per kilowatt hour. So when it comes to utility costs here in California, especially if you are in an area where it's an investor-owned utility, an IOU, electricity costs are just absolutely off the charts. This is several times higher than the American average, and this is despite the fact that California has rolled out more renewable energy than any other state in the past couple of years here, and also despite the fact that solar and onshore wind, when it comes to the cost of electricity, the production cost per kilowatt hour, onshore wind and solar is the cheapest out there. So instead of our electricity rates going down, it has actually gone up, and it has gone up quite a bit, in fact. So that's why, again, for a lot of my followers who actually do live on the grid in California, we're trying to figure out ways to reduce their costs. One of the easiest things is obviously to deploy solar and store that energy somehow in an energy storage system. And if you guys have been following my live streams on TikTok, you know I do have a website at allthingsoffgrid.com, and you can go over there for a sign-up sheet to purchase batteries directly from me, and you can get good quality cells, and we walk you through how to DIY and build your own pack and hook it up to charge controllers and inverters, so you can have a resilient power system for whether you're off the grid or on the grid. So those are some of the things that we cover on our channel here. But two of the interesting things that have come up in the last couple of months here is, one of them is sodium ion batteries. The other is zinc batteries. There's zinc air and zinc bromide. Sodium batteries, now, it's not particularly new. If you look at this chart over here on the left, I suppose, you can see that lithium-ion batteries were originally developed in the 70s, whereas sodium-ion batteries are really developed in the 80s. So there's a bit of a lag there, about 10 years. When it comes to where we are as far as the capabilities of sodium-ion batteries, obviously it is definitely behind compared to lithium batteries. Just also taking into consideration that there is almost a 10-20 year lag in terms of development and commercialization versus lithium and sodium batteries. Now, a lot of people have fear that there's not enough lithium out there for all the cars to be switched over to EVs. That couldn't be further from the truth. there is plenty of lithium out there. So even if you take this chart here into consideration, it says here that sodium crustal abundance is at 2.75%. It's everywhere. The price is $3 per kilogram, whereas lithium is 0.0065%, and 75% of America's $20 for lithium cobalt oxide. So that's what they claim, but when it comes to the actual availability of lithium, the fact of the matter is there's plenty of it out there. It's something that you can extract from seawater as well if you really wanted to. Again, that's a more expensive way to extract it, but there are plenty of resources out there. Even here in California in Salton Sea, there's enough lithium out there for dozens of millions of cars. Thacker Pass over in Nevada, I think there's enough out there for several hundred million EVs. So again, when it comes to lithium shortage, a lot of places out there in the media like to run with that story and run with that notion, but when it comes to reality, there is plenty of lithium available out there, and I don't think we're going to be running into a shortage anytime soon. Now, having said that, lithium batteries, there are multiple chemistries out there, and that's where it gets a little trickier, because now if we're talking about, for example, lithium cobalt oxide or NCM, NCMA batteries, where you have to have cobalt into the mix. Cobalt is definitely one of the more rare metals out there, and there is some controversy in terms of mining practices for cobalt, and it does come primarily from Africa right now. So that's that has nothing to do with the lithium itself, but it is certainly something to consider in terms of the long-term viability of lithium batteries. Now, again, having said that, here in America, most of our EVs are powered by NCM or NCMA batteries. NCM and NCMA batteries typically tend to have higher energy density and specific power density compared to other lithium chemistries. So when it comes to performance, especially in an electric vehicle where you have limited amount of space and you want to reduce the mass as much as possible, here in America, almost all of our electric vehicles are powered by those two chemistries when it comes to battery technologies. Lithium iron phosphate, here in the US, we don't really produce any LFP batteries. Vast majority, I would say, venture to say 99% plus is manufactured in China right now. And as far as the R&D and the supply chain, it completely revolves around China right now. Having said that, LG Energy, they are setting up a battery factory in Arizona right now, in the process of going under construction, and it will be a 14 gigawatt hour ESS LFP plant. So there will be some LFP production being done in the US in the near future. There was also talks of a joint venture between CATL and Ford. I'm not sure if that's going to go forward because, again, it's a Chinese company, and as far as the Inflation Reduction Act, most of that is going to be towards companies that produce in the U.S. And despite the fact that that joint venture would have a factory here in the U.S., all the materials will still come from China. So that's where it will get really tricky for American production of LFP cells right now. Now, LFP, lithium iron phosphate, the other materials that are involved with the production of those batteries, the iron and the phosphates, are readily available. It's certainly a lot cheaper than NCM and NCMA chemistry. NCM, it's nickel, cobalt, manganese, and NCMA includes aluminum. NCMA is pretty much exclusively used in Tesla and their Model S, their Model 3 and the Model Y. They are in the process of deploying some NCM cells for their power walls because NCM has better cycle life than NCMA, but when it comes to absolute performance, NCMA is a little better than NCM cells. So that's why Tesla has been very eager to adopt the NCMA and NCMA chemistry in their vehicles. Now, When it comes to, especially those of us who live off the grid, none of that matters too much. We don't have limitations in terms of space usually, and we certainly don't really care about weight that much because these batteries are going to be stationary. So for those of us who live off the grid, the LFP or iron phosphate cells are definitely the way to go right now when it comes down to cost. The other unique thing, and the other reason why LFP is very common and popular for us off-gridders, is the fact that when it comes to voltage compatibility, LFP is very comparable to 12-volt base systems that are legacy systems from lead-acid batteries. So, we talk about battery technology and how it's evolved over the years. So, lead-acid batteries have been around for a very long time. I mean, it's been commercialized since the 1880s. When they first utilized lead-acid batteries for starting vehicles in the early 1900s, they used 6-volt batteries. Right around 1950s, these vehicles started having transistor radios, lights, a lot more additional accessories, and they require a little more oomph to power all those devices. So that's where they made that transition from 6 volts to 12 volts. And basically after that point, there were other, for example, diesel, large diesel vehicles, trains, things of that nature that required multiples of 12 volts to start the engine. So that's why 24 volts came along, and from there on out 48 volts came along. And there are other solutions out there that are multiples of 12 volts, but most commonly for us off-grid folks, 24 and 48 volts. In fact, 48 volts would be where I would recommend if you're going to be off the grid in a regular home. If you're in an RV size vehicle, then you can probably get by with something a little smaller, but for the vast majority of people out there who are living in cabins or a nice size home, 48 volts is really the sweet spot for you to power your home. Now, that's going a little into the history of lead-acid batteries. And so what does that have to do with the lithium batteries? Well, lead-acid batteries, each cell is roughly around 2.1 to 2.2 volts. And so if you have 6 of those cells, a fully charged lead-acid battery should be right between 12.8 to 13.2 volts. And to get a lead-acid battery to fully charge, you need to have a charge voltage of roughly around 14.4 to 14.6. Some chemistries can go a little higher, but that's the usual range. Now, with lithium iron phosphate cells, the nominal cell voltage is between 3.2 to 3.3 volts on average, and it takes a 3.6 to 3.65 volts for a maximum charge. Now, 3.6 times 4 just happens to be 14.4. 3.65 times 4 happens to be 14.6. So it's by coincidence, it just happens to overlap with the max charge voltage of a lead-acid battery, for a 6-cell lead-acid battery, for a 4-cell lithium iron phosphate cell, battery. And when you actually have the battery in use, the LFP battery is going to drop down to about 13.2 volts under 13.2 to 12.8 volts under normal operation, which is again right within the range of lead-acid batteries. So it's just by sheer coincidence that you can pretty much utilize a 4-cell lithium iron phosphate battery as a drop-in replacement for a 6-cell lead-acid battery, and that's why it became popular to utilize lithium iron phosphate cells for 12 volt, 24, and 48 volt applications. Now, along comes sodium ion batteries, and despite the fact, so if you look at this chart here, it says the advantage of sodium ion batteries is low cost. This chart right in the middle here, you can see that there is potential cost reduction with sodium ion battery, and you see there most of it is on the cathode side. In fact, on the anode and the electrolyte and the separator, on the rest of these BOM materials, it's not much of a difference. So Just because you replace the lithium with sodium does not equate this drastic reduction in battery costs. There's still a lot of other processes that are involved in manufacturing these cells. So again, if you take into consideration how much lithium actually goes into a standard lithium ion battery, it's not much. For example, a vehicle the size of a Model S, which is an 80 kilowatt hour pack, or a Model 3, which is a 60 kilowatt hour pack, there's only about 10 to 15 pounds of actual lithium in there. So when it comes to the cost of the raw lithium for the actual battery, it's not much. And just by switching that out to sodium, despite the fact that sodium and the cathode materials for sodium-ion batteries is somewhat cheaper than lithium batteries, you still have to manufacture the cell. There's a lot of other materials that are involved, and those are not costs that you can really effectively cut down in the manufacturing process. So that's why you don't see too much cost savings when it comes down to sodium-ion cells. In fact, we've been going back and forth between China to see where costs are for the production of sodium-ion batteries, to see how it compares and how it fares compared to lithium iron phosphate cells. And in fact, right now it's actually more expensive to manufacture sodium-ion cells versus lithium iron phosphate cells. To the point, it's actually about 20 to 30% more expensive. So at this very moment right now, there are no cost savings to be had by switching over to sodium-ion batteries. Now, can that change over time? Absolutely. But the biggest challenge for sodium-ion batteries is, if you look at who the biggest manufacturers of LFP batteries are, it is definitely all the Chinese. The Koreans and Japanese have almost zero production when it comes to LFP chemistry cells right now. So again, as I mentioned earlier, 99% of all LFP batteries are manufactured in China right now. And the incumbents, for example, CATL, BYD, and there's a couple other smaller companies that make up the supply chain in China right now. They've invested billions and billions of dollars to scale up their factories for the production of LFP cells. So companies like CATL, they're close to 0.5 terawatt hour of LFP production capacity right now. They actually have the know-how to manufacture sodium-ion batteries right now, but if you were in their shoes, would you invest money in this chemistry that would, one, basically negate all the money that you've invested in LFP production? And the answer is no. So when it comes to the production of sodium-ion cells, it wouldn't be in the interest of existing lithium battery manufacturers to convert and switch to sodium-ion battery production. So there's companies like CATL, Northvolt. You'll find some information about sodium-ion cells on their website as well. But Northvolt, they're a European company. They don't really have that much background when it comes to actually manufacturing any of these batteries. It's just a consortium that he put together to try to produce some cells in Europe right now, and between the costs of manufacturing in Europe, despite the government subsidies that they're getting, they're not very cost competitive as well compared to the Chinese or the Koreans. But so the page that you see here is from Haina, which is one of the companies that have actively been investing in developing sodium-ion battery technology. The founder of that company actually was the mentor for the founder of CATL, so there's some relation between the two companies there. And the nice thing about Haina is the fact that they don't have legacy lithium battery production, so they have nothing to worry about in terms of cannibalization of their sales. So that's why this company is getting subsidies from the local provincial governments in China. They're getting support to manufacture these cells, because the one thing that's inherently unique about sodium-ion cells, at least why the Chinese are investing so much money into it right now, is the fact that they can completely control the supply chain from the beginning to the end. So when it comes to lithium batteries, when it comes to lithium iron phosphate cells, they can control that in a little better They can control that a little more tightly, but when it comes to NCMA chemistries, they still have to import some of these materials from other countries, and so they're reliant on importing parts and components from other countries to manufacture those cells, whereas if they switched over to sodium ion cells, they can completely vertically integrate within China. So that's the objective when it comes to manufacturing sodium ion cells in China, and that's why, despite the fact that cells cost 20 to 30% more to manufacture compared to lithium iron phosphate cells right now, the local governments there are actively promoting and subsidizing the production of these cells, because in the long run, the Chinese, definitely compared to Americans, they do tend to take a longer term view on these type of technologies. And when it comes to renewable energy, transforming and becoming green, batteries are probably the biggest part of that. When it comes to producing power, obviously there's tons of money that's invested in solar, there's tons of money that's invested in wind, there's a lot of other viable technologies out there, but when it comes to renewable energy, most of it is intermittent, and without the use of batteries, those the power that you produce from these renewable energy sources, you've got to save them somewhere. So again, the Chinese are very forward thinking when it comes to investing in these technologies and the direction of where the world's economy is going when it comes to producing and storing energy. So again, if we look at this chart here right now, you can see on the far left, that's a chubby guy there, that's to represent lead acid batteries. The one in the middle is sodium ion batteries. The one on the right is lithium ion batteries. You can see that the performance, the energy density, and the voltage and the life of lithium batteries is definitely higher than sodium ion batteries at this very moment. Now, again, having said that, we're still about 10 to 20 years behind right now in terms of the development process of sodium ion batteries. So there's still plenty of room for sodium ion batteries to improve, and that's not to say that there isn't room for lithium batteries to improve either. So that's always been a challenge that I've seen. I've been going to RE Plus for years. Well, it was named something else prior to their rebrand. But if you've been following these different shows, a lot of companies were really trying to target lithium batteries when it came down to the cost per kilowatt hour of storage. And many companies have failed in the past 10 years. And the biggest reason why is, well, it's 2024 now. Back in 2010, lithium batteries were over $1,000 per kilowatt hour. At the time, a lot of these other incumbent, new entries for the renewable energy storage manufacturers, they were targeting energy storage costs between $200 to $300 or $400 per kilowatt hour. Fast forward 14 years now, when it comes to cell costs directly out of China right now, it is close to approaching $50 to $60 per kilowatt hour right now. So there's been a 20-fold drop in the cost of lithium batteries per kilowatt hour in the past 14 years. So if you were a company that was developing flow batteries or any of these other chemistry batteries, and you were targeting being competitive with lithium batteries at $200, $300, $400 per kilowatt hour, basically your company's ruined right now, because lithium batteries are substantially cheaper than that. So that's why a lot of different companies have gone out of business. So the big question mark right now is, can sodium batteries really make a difference and really make an impact when it comes to energy storage, when it comes to automotive use, when it comes to all these various different uses for energy storage? And it's a huge question mark. Nobody really has the answer for that right now, because there's a lot of different factors at play. So we do have some sodium ion cells here. This right here is a 54 watt hour 46145 cell. If you guys know anything about the Tesla, the Cybertrucks, they're using a 4680 cell. Basically, the diameter is about the same as this cell right here, but it's 8 centimeters tall, whereas this one is 14.5 centimeters tall. So a Tesla 4680 cell would be about that round and that tall, whereas this one is quite a bit bigger than that. And again, this one is 54 watt hours. I don't remember the capacity of the Tesla's 4680 cell off the top of my head here, but let me just check what the 4680 amp hour is. It's 22.3 amp hours for a Tesla 4680 cell. So if you multiply that by the fact that it's about 3.7 volts per cell, then it would come out to, let's see here, 23.3 amp hours times 3.7 volts. You're looking at about 86 watt hours. This one is substantially bigger than that, and it's only 54 watt hours. So again, when it comes to energy density, no one's questioning whether or not NCMA cells are better. They absolutely are. But if we take into consideration that the NCMA cells can be quite explosive and quite dangerous, that's where these type of other chemistry cells start making more sense there. Now, when it comes to sodium ion cells, they can be made in various form factors. This is obviously a cylindrical cell. I do have sodium ion pouch cells and prismatic cells here as well. When it comes down to how they look, I mean, it's just like any other lithium battery. I mean, this is what a pouch battery would look like regardless of what kind of chemistry you have, whether it's iron phosphate or NCM or sodium ion for that matter. And we also have prismatic cells like this. This one right here is also an LFP cell, but they do make prismatic cells and other chemistries as well. So again, the form factor doesn't matter too much when it comes to the production of these cells. One thing to note with the performance of these batteries is the energy density is on average about 30%, 40% lower than even lithium iron phosphate cells. So I have gone through various different lithium iron phosphate cells out there and NCMA cells. There's no doubt in my mind that sodium batteries are not really competitive. I mean, if you take into consideration that we don't even have iron phosphate cells for EVs here in the US, we're not going to have sodium battery powered cars in the US anytime soon. I mean, they do have one model that they deployed in China right now, and in the Chinese market, if you can get the cost down enough, there's definitely a market for people who want cheaper cars. So there's a demand there, but here in America, that's just not going to fly because the range is going to be so short with these vehicles. But you know, in the course of the next 5-10 years, can they actually bring down the cost? Again, it's the big question mark. So when I spoke to the representative at Haina, they were in the process of making a pilot production line, which is supposed to be 3 gigawatt hours. 3 gigawatt hours for any new battery technology is substantial in size, but for lithium batteries, lithium battery factories, 3 gigawatt hours is a drop in the bucket. I mean, if you take into consideration that the average production line from CATL, BYD, LG, SK, or Samsung SDI, or Panasonic, Tesla, these companies are building factories that are 20, 30, 50 gigawatt hours in size. So a 3 gigawatt hour battery production line is fairly small by today's standards, but I mean, you got to start somewhere. And once they build a production line that's 3 gigawatt hours, they do think that it would be cost competitive with LFP cells, which is pretty impressive if you take into consideration there's over a terawatt hour of iron phosphate cell production capacity worldwide right now. So with a small 3 gigawatt hour production line, they can try to be cost competitive with LFP, which is quite impressive in my opinion, and it will only go down from there once they continue scaling up. Now again, the performance is not that great. The biggest problem I've had with sodium batteries is when I mentioned the voltage range for LFP batteries earlier, a fully charged LFP battery is about 3.6, 3.65 volts. Fully depleted battery is typically somewhere between 2 and 2.5 volts. If you drop it below 2 volts, you will start incurring damage to the cells. So frankly, I don't even recommend you bringing it down to 2.5 volts. So about 2.75, 2.8 is where I would really try to limit the battery voltage on an LFP cell. So again, the operating range, as I mentioned, is 2.7 to about 3.6. The problem with these sodium ion cells is the max voltage charge on these is 3.95 to 4.0 volts, and the cutoff voltage is as low as 1.5 volts. So if you have a 4-cell LFP battery, you're talking 2.75 volts. The low voltage cutoff is 11 volts. And if you're talking 3.65 volts, then your high voltage cutoff is 14.4 to 14.6 volts. The problem with sodium ion cells is if you had a 4-cell battery, you would need 16 volts to fully charge the battery pack, and your electronics would have to be able to withstand a voltage as low as 6 volts to take advantage of 100% of the battery's capacity. Again, fully charged, 4 volts per cell. Fully depleted, 1.5 volts per cell. So I mean, that's a huge wide range. Any 12 volt inverter out there, they will stop working right at around 10 volts. Most will not even power on. Your car will certainly not power on anything under 10 volts. So again, if you had a 4-cell sodium ion battery, and if you're trying to use the capacity of the sodium ion cell, you'd only be able to use 20, 30, maybe 40% of the battery's capacity in a regular 12 volt system without having to redesign all of your electronics, whether it be the inverter, charge controllers, or any other devices that you have connected to it. So without a complete revision on the power electronics side of the devices that you're running, sodium ion cells right now certainly can't take off. So despite the fact that there are companies out there that are selling 12 volt sodium batteries right now, the problem right now is we just can't get practical applications for 12 volt batteries, sodium ion batteries, for the average user. So there's definitely a challenge there, which can it be solved over time? It certainly can be, but at this very moment, it's certainly not a drop-in replacement for 12 volt batteries that lithium iron phosphate cells are right now. So again, there needs to be a lot of engineering resources that are applied towards these devices. So again, in the next 5 to 10 years, can we see more devices that can handle that? Possibly. I'm starting to see more and more companies come up with solutions where you can customize and dial in the voltage range of the devices that you're trying to operate. There are some charge controllers out there, and there are some inverters that have wider operating voltage ranges. So as these companies start producing more and more options where you can actually dial in the operating voltage range of their devices, you will see more and more of these other battery chemistries start taking off once the costs come down. Again, we're not quite there yet, but the possibility is definitely there in the next 5 to 10 years. So that's where things are with sodium ion cells right now. We will definitely talk about them in more depth in one of my future live streams. Again, we do a lot of the testing here, not just at my facility here, but we do have a facility over in China, in our own labs, where we do cycling tests of all of the batteries that go through our facilities here. Unfortunately, I didn't have time to go into the zinc batteries that I really wanted to share, but we'll cover that in another session in the near future here. So that's all for now, guys. Catch us again in the near future. Like, subscribe, and share our content with others, and hopefully we can get this up and going just like we had on TikTok not too long ago. So again, thanks for your support, and I hope to see you guys again soon here.